Thank you for giving me opportunity to talk. The title is An Adjunction Inequality for Powerful Type Invariants with Application to Sliceness and Four-Dimensional Topology. So I'm Masaki Taniguchi working at Riken in Japan. And this is joint work with Nobuo Ida and Anham Mukherjee. And for more details, you can see this archive for our joint work. And today we have 4 parts. The first part is backgrounds. We will focus on sliceness of nodes in this talk. In the second part, I will give the main theorem in this talk. In the third part, we will introduce some tool to obtain our main result, which is called powerful type invariant. And at the end of this talk, I will give a proof of main theorem. So let's go to the first background. So today we will focus on the sliceness of nodes. So let me recall what is the definition of slice. So let K be a node in S3. And it is slice if there exists smooth embedded disk, two-dimensional embedded disk D2 in D4, such that the boundary of D2 is equal to a given node K. So this is a definition of slice. So picture is this. So as a boundary of D4, you have S3. And on the boundary, you have a node K. And if this K bounds some disk like this, then it is called, such a node is called a slice node. And if this embedding is locally flat topological embedding, then such a node is called topologically slice node. And there are many studies of sliceness of nodes, but today we focus on the sliceness in general for manifold instead of D4. So let X be a connected and closed smooth form manifold. And again, we consider a node in S3. And K is called H slice in X. If there exists a smooth null homologous embedded disk D in X minus small open ball, then it is called H slice. The point is that we are assuming that the disk is null homologous. And topologically slice is defined by similar way. So this is locally flat topological embedding. So this is an important notion in today's talk. Sorry, I should say the boundary of D2 is equal to K. So this is the definition of H slice. And our main result gives new obstruction to H sliceness in certain class of four manifolds. So let me say the fundamental fact. So if K is H slice in S4, then this implies K is actually slice in usual meaning. Moreover, these conditions are equivalent. So this means H sliceness gives a generalization of sliceness in some sense. And note that a usual adjunction inequality cannot be used to obstruct H sliceness. Because the homology class is 0. So we need to consider other technique to obstruct H sliceness. So first, I would like to review the known obstruction to H sliceness. I would like to say the topological obstruction at first. So obstruction to topological H sliceness. For example, signature function, or Rohorin type theorem. Are known obstruction. And today we focus on the obstruction to smooth H slice. And for such, And for indefinite form manifold, so H sliceness in definite form manifold. So definite means the intersection form of four manifolds are definite. For such manifolds, the Higard-Freer-Tau invariant gives some obstruction. So this is some famous obstruction introduced by Odbas and Szabo. Also, TB number, Thurston-Benecon number, gives a lower bound of the tau invariant. So which is proved by Pramine square. Also, some concordance invariant from not instant Fourier homology. So this is defined by Kronheim and Moroka. And in covariant homology theory, Rasmussen invariant gives an obstruction for the connected sum of CP2 or connected sum of CP2 bar. So this is proved by Manoles-Kumarengon circles. Yeah, these are famous obstructions for H-sliceness, to H-sliceness in definite form manifold. Okay. Yeah, also, I should say the local equivalence class invariant from which are obtained from the instant not Fourier homology or Higa not Fourier theory. Gives our obstruction. So this is some generalization of previous numerical invariants. So actually there are many studies of sliceness of knots. And today we also consider indefinite form manifold. So we will focus indefinite form manifold. For such a manifold, there are not so many obstructions to H-sliceness. So the famous obstructions are generalized Thurston-Benecam inequality, proved by Murok and Rowling. Also recently, Manoles-Kumarengon gave some obstruction of H-sliceness from Bauer-Fulda type invariant. So Manoles-Kumarengon. Also in that paper, they also gave some 10/8 type obstruction. So this is coming from 10/8 inequality proved by Fulda. And by using these obstructions, Manoles-Kumarengon proved the following interesting result for H-sliceness. So they proved that for the right hand trefoil, handed trefoil, K is H-slice in the connected sum of 3 copies of CP2 and 20 copies of CP2 bar, but K is not H-slice in blow-up of K3. And it is known that these manifolds are exotic pair. So these are exotic. So this result gives a relation between the smooth structure and H-sliceness. So this is a review of H sliceness. So next, I would like to talk about our main result. So let's go to the second part. So main result. So we gave some new obstruction to H sliceness in certain class of form manifolds. So let K be a knot in S3. And suppose the Thurston Benecke number of K is positive. Then K is not H slice in any closed and symplectic form manifold with satisfying B10 and B plus is congruent to 3 or 4. Here B plus is the number of positive eigenspace of the intersection form of a given form manifold. So this is the main result in this talk. So this gives some new obstruction to H sliceness in a certain class of symplectic form manifolds. So first, I would like to explain what is TBK, so certain Benecke number of a knot. So the TBK is called maximum certain Benecke number. So let me recall the definition. So TBK is given by the maximum of the difference between the Seifert framing and contact framing over the all Legendrian representation. In the S3 with standard contact structure. So the Legendrian means the representative of K such that the tangent of K is included in the two-plane field Z, and the disk Z is defined as the intersection of TS3 and JTS3. Here, J is a complex structure on C2. And here, the contact framing is the framing coming from the inclusion, this inclusion. So this gives a contact framing. And we take the difference between the Seifert framing and contact framing. And we take maximum. And this gives an isotopy invariant of K. Okay, so let me say the calculation is several calculations of certain Benecke number. So let TPQ be a positive torus knot. This, and then it is computed that TB number for PQ torus knot is equal to PQ minus P minus Q. And this is proved by Etonayer and Honda. And this is equal to p minus 1 times q minus 1 minus 1. And this is always positive. So this satisfies our assumption. And in order to consider interesting sequence of knots, we consider the whited double. So let K be a knot in S3. So what is whited double? So whited double is the satellite knot. Of K with respect to the pattern given by, which is given by this way. Okay. And it is not so difficult to check that if the Sanson-Meneka number is positive, then the TB number of the whited double of K is also positive. And actually, there is some diagrammatic method to describe Legendre knot, so-called front projection. And by using front projection, TB number is easily estimated. So by using such a method, we can conclude this result. So this is followed by the front projection. Okay. So, and by using these examples, I would like to give some concrete application of main result. So, yeah, one can prove the following result. So there exists a sequence of knots Ki such that the first condition is Ki not H slice in the K3 surface. But Ki topologically H slice in K3. Also, Ki a slice in K3. So this means if you don't assume any condition on the slice disk, homological condition on the slice disk, then it admits a properly embedded disk in K3. And the first condition is Ki are linearly independent. In the not concordance group. Okay, one can prove this result from our main result. So yeah, I will explain how to obtain such a result from main theorem in the second talk. Okay, so thank you for listening to the first talk. So that's all of my first talk. And thank you very much.